Reynolds apparatus. Theory. Depending on relative magnitudes of viscous and inertial forces, flow can occur in two different manners, like laminar flow and turbulent flow. In laminar flow, viscous effects are predominant than the inertial effects, but when shear and normal stresses are added with increase in velocity of flow, the flow is turbulent. The motion is laminar or turbulent according as the value of R is less than or greater than a certain value. If a liquid such as water is allowed to flow through a glass tube, and if one of the liquid filament is made visible by means of dye, then by watching this filament we may get insight into the actual behavior of the liquid as it moves along. After the water in the supply tank has stood for several hours to allow it to come to completely to rest, the outlet valve is slightly opened. The outlet valve is slightly opened. The center thread of dye carried along by the slow stream of water in the glass tube is seen to be nearly as steady and well defined as the indicated column in an alcohol thermometer, but when, as a result of further opening of the valve, the water velocity passes a specific limit, a change occurs. The rigid thread of dye begins to break up and to group momentarily ill-defined. The movement of the dye deviates from its straight line pattern corresponds to the condition when the conduit is no longer in laminar condition. The discharge Q flowing in the conduit at this moment is measured, and the Reynolds number Re is equal to 4Q by pi dV, in which d is the diameter of the conduit and nu is the kinetic viscosity of water, is computed. This is the lower critical Reynolds number. Finally, at high velocities, the dye mixes completely with the water and the colored mixture fills the tube. Objectives: to study different flow conditions. Second, to obtain the Reynolds number in different flow conditions. Experimental setup. This is dye container, this is supply tank, this is Perpex tube, this is valve to control flow, this is filament of dye, this is bell mounted entrance, this is supply tank, this is Reynolds apparatus for demonstration of the laminar and turbulent flow. Suggested experimental work. Step 1. Note down the relevant dimension as a diameter Perpex tube, area of collecting tank, room temperature, etc. Step 2. By maintaining suitable amount of steady flow in the Perpex tube, open inlet of the dye tank so that dye stream moves as a straight line in the tube. Step 3. The discharge flowing in the Perpex tube is recorded. Step 4. This procedure is repeated for other values of discharge. Step 5. By increasing the velocity of flow in the Perpex tube, again open the inlet of the dye tank so that dye stream begins to break up in the tube, which shows the fluid is no more in the laminar condition and transition stage occurs. Step 6. The discharge flowing in the Perpex tube is recorded. This procedure is repeated for other values of discharge. Step 8. On further increase in velocity of flow in the Perpex tube, again open the inlet of dye tank so that dye misses completely in the tube which shows the fluid is no more in the transition stage, hence turbulent flow occurs in the tube. Step 9. The discharge flowing in the Perpex tube is recorded. Step 10. This procedure is reported for other values of discharge. Results and discussion. Calculate discharge in different flow conditions. Also calculate Reynolds number for different flow conditions. Sample data sheet. Inner diameter of conduit d mm is equal to 25. Room temperature at theta degrees Celsius is equal to kinetic viscosity of water nu centimeter square per second is equal to 1.14 into 10 raised to minus 4. Area of collecting tank centimeter square. Serial number, discharge measurement, initial centimeter, final centimeter, time taken seconds. Discharge Q centimeter cube per second. Re is equal to 4Q by pi dV. Apparatus for verification of Bernoulli's theorem. Objective: to verify Bernoulli's theorem experimentally. Note, note this is inflow, this is supply tank, this is piezometer tube, this is Perpax duct, this is sporting stand. Operators for the verification of Bernoulli's theorem. This is outflow. This is apparatus for verification of Bernoulli's theorem. The experimental setup consists of horizontal Perpax duct or smooth variable cross section. Apparatus for verification of Bernoulli's theorem. The experimental system consists of horizontal Perpax duct or smooth variable cross section of convergent and divergent type. The section is 40 mm into 40 mm at the entrance and the exit, and 40 mm cross 20 mm at the middle. The total length of duct is 90 cm. The piezometric pressure P at the location of the pressure tapping is measured by means of 11 piezometric tubes installed at an equal distance of 7.5 cm along the length of conduit. The duct is conducted with supply tanks at its entrance and exit ends. The duct is connected with supply tanks at its entrance and exit end with means of varying the flow rate. A collecting tank is used to measure the actual discharge. This theory consider frictionless flow along a variable area duct. The law of conservation of energy states for an inviscid, compressible, irrotational and the steady flow along a streamline, the total energy overhead remains the same. This is called Bernoulli's equation. This is graphical presentation of Bernoulli's theorem. This is Z1, this is P1 by W, this is V1 square by 2G, this is V2 square by 2G, this is P2 by W, this is Z2, any datum, Z3, this is P3 by W, this is Vc square by 2G, this is C. This is graphical representation of Bernoulli's theorem. The total head of flowing fluid consists of pressure head, velocity head and the elevation head. Hence, P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2, where P, V and Z refers to pressure, velocity and position of the liquid relative to same datum at any section. Suggested experimental work. Note down the piezometric distance from the inlet section of the Perpax duct. Step 2. Note down the cross-sectional area of Perpax duct at each of the piezometric apping points. The datum head is stated as constant throughout the duct. Step 4. By maintaining the suitable amount of steady head or nearby steady head conditions in the supply tanks, there establish a steady non-uniform flow in the conduit. The discharge flowing in the conduit is recorded together with the water levels in each piezometric tubes. Step 6. This procedure is repeated for other values of discharge. Results and discussions. If V is the velocity of the flow at a particular section of the duct and Q is the discharge, then by continuity equation V is equal to Q by area of section. Second, calculate velocity head and total head. Plot piezometric head P by W plus Z, comma velocity head V square by 2G. Total head P by W plus Z plus V square by 2G. Versus distance of piezometric tubes from same reference point. Sample data sheet. Area of collecting tank centimeter is equal to increase in depth of water centimeter times second. Discharge centimeter cube per second. Tube number. Distance from inlet section centimeter. Area of C over S of conduit A centimeter square. Velocity Sudden contraction from 50 mm to 25 mm diameter. Pressure tappings are provided on the tip stream and downstream ends of each of these fittings to enable the measurement of pressure head difference across the fittings to compute the head loss through the fittings. The pressure tappings are connected to a differential manometer. A Eclatin tank is used to find the actual discharge of water through the pipe fittings. Theory: in long pipes, the major losses of energy in pipe flow is due to friction, while the minor losses are those which are caused on account of the change in the velocity of apparatus. For determination of loss in pipe fittings, aim to determine the minor head loss coefficient for different pipe fittings. Experimental setup: the experimental setup consists of a pipe circuit of 25 mm diameter fitted with the following fittings with mean of varying flow rate: large band, sudden enlargement to 50 mm diameter; small band. Fourth, sudden contraction from 50 mm diameter to 25 mm diameter. Pressure tappings are provided on tip stream and downstream ends of each of these fittings to enable the measurement of pressure head difference across the fittings to compute the head loss through the fittings. The pressure tappings are connected to a differential manometer. A Eclatin tank is used to find the actual discharge of water through the pipe fittings. Theory: in long pipes, the major loss of energy in pipe flow is due to friction, while the minor losses are those which are caused on account of the change in the velocity of flowing fluid, either in magnitude or direction. Losses due to change in cross section, bends, walls, and fittings of all types are categorized as minor losses. In short pipes, above losses may sometimes outweigh the friction losses. The minor energy head loss HL in the terms of velocity head can be expressed as HL is equal to K into V square by 2G, where K is the loss of coefficient, C which is practically constant at high Reynolds number for a particular fluid geometry, V is the velocity of fluid in the pipe, and G is the acceleration due to gravity. However, for a sudden enlargement of the section, the simultaneous application of continuity, Bernoulli's and momentum equation showed that St is equal to K V minus V square by 2G, where V and Vt are the velocity of flow in the smaller and larger diameter respectively. Suggested experimental work or procedure. Step 1. Note down the relevant dimension of each dimension, fittings, area of Eclatin tank, etc. Step 2. Pressure tappings of fittings are kept open, while for other fittings it is kept closed. Step 3. The flow rate is adjusted to its maximum value by maintaining suitable amount of steady flow in the pipe circuit. There establishes a steady non-uniform flow in the circuit. Time is allowed to stabilize the levels in the two lines of the manometer. Step 5. The discharge flowing in the circuit is recorded together with the water levels in the two lines of manometer. Step 6. The flowing is reduced in stages by means of flow control value, and the discharge and the readings of manometer are recorded. Step 7. The procedure is repeated by closing the pressure tappings of the fitting together with other two fittings and get opening of another let fitting. Result and discussion. Step 7. The procedure is repeated by closing the pressure tappings of this fitting together with other two fittings and for openings of another let fitting. Results and discussion. Fill out the data sheet. Calculate the discharge difference of manometer reading and K loss coefficient for different pipe fittings for different sets of manometer. Third, find the average loss coefficient K. Precautions. Apparatus should be in the leveled condition. Reading must be taken in steady or nearby steady conditions. Third, there should be no air bubble in the manometer. Experiment 7. Stokes law apparatus. Theory: when an object is placed in a fluid flow, a force is exerted on the object by the flow. This force is due to the frictional effects combined with the difference in pressure on the two sides of the object. The component of this force in the flow direction is called a drag force, and that's expressed as F is equal to CD into A into rho V square by 2, where F is the drag force, CD is the coefficient of drag, V is the mean velocity of the body through the stationary fluid, A is the projected area of the object of the plane, normal direction of flow, and rho is the mass density of the fluid. The coefficient of drag CD varies with Reynolds number for a given shape of the object. One can expect similar behavior to hold in a case in which the fluid is stationary but the object is moving. Consider a sphere of diameter d falling in an infinite fluid whose mean density is rho with a constant velocity v called the terminal velocity. The drag force exerted by the fluid is equal to the submerged weight of the sphere. Thus, F is equal to CD into pi d square by 4 into rho v square by 2 is equal to pi by 8 pi by is equal to pi by 6 d cube g into rho s minus rho f, where rho s and rho f are the mass densities of the materials of the sphere and the fluid respectively. However, if the fall velocity of the sphere is such that the Reynolds number Re defined as Vd by rho is less than 0.2, then a drag force is obtained by Stokes by solving the equation of motion. Navier-Stokes equation is expressed as F is equal to 3 pi d mu v. From equation 1 and 2, for Re less than 0.2, CD is equal to 24 by Re. The above equation hold good only for spherical particle falling in an infinite fluid medium. If the spherical particle falls in a finite fluid medium, then the observed fall velocity v is corrected using the following expression in order to get the fall velocity corresponding to infinite fluid medium. V is equal to v dash into 1 plus 2.4 d over d dash, where d dash is the diameter of the container.